Section 4.1 Polynomial Functions. Our objectives are to define a polynomial function, to divide polynomials, to apply the remainder theorem, the factor theorem, and the connections between the remainders and factors, to determine the maximum number of zeros of a polynomial function. Let's start off with our polynomial function. So let's say that this equation that we have right here at the top is a polynomial function where n is a non-negative integer, x is a variable, and a sub 0, a sub 1 to a sub n is a constant called the coefficient. A sub 0 is the constant term. For something to be a polynomial equation, all exponents have to be whole numbers. No variables can be in the denominator, and also there can be no variables underneath a radical. So looking at these equations, it says, are the following polynomial functions? If we look at the first one, notice that there are no variables in my denominator. There are also no variables that are underneath a root, and their exponents are all whole numbers. Therefore, this is a polynomial equation. The next one, all of those pass as well. So yes, this is a polynomial equation. 12 doesn't have any variables. This is just what we call the constant polynomial. So yes, this is a polynomial equation. Right here we have a radical, but however, notice the variable is not underneath the radical, just root 20. And we also have a fraction, but there is no variable in my denominator, so this would also be a polynomial equation. X to the negative 2, however, if you remember, this is not simplified. It would be 1 over x squared if you remember your properties of exponents. Thus, this is not a polynomial because it has a variable in the denominator. For the next one, we have 2x to the 1/3. So remember that this is a rational exponent, which can be written as 2 times the cube root of x, and now because of that, and because the exponent is not a whole number, I know this is also not a polynomial. The next one I have m plus the square root of m, and again, because there's a variable underneath a radical, this is not. And for the last one, I have a variable in my denominator, so this is also not a polynomial equation. So the zero polynomial we have is just 0. The degree of a polynomial is the exponent of the highest power of x that appears with non-zero coefficients, and that becomes the degree. The non-zero coefficient of the highest power is also called the leading coefficient. If we look at these polynomial equations that we have right here, we want to write the degree, the leading coefficient, and the constant term. Normally, if we're writing the polynomial degree, you would first want to make sure that it's written in order with each term. So each term is separated by addition or subtraction signs. So right here we have 1, 2, 3, 4, 5 terms. And you want to write it in order with the highest exponent first, which in this case is 7. So since that's the highest exponent, this would be a degree of 7. And then you look at the number that is in front of the x to the 7th power, so the coefficient is 6. So that is what we call our leading coefficient. So the leading coefficient would become 6, and the constant in this case is the one that does not have a variable attached to it, so this would be 10. For the next equation, x cubed, I only have one term, and it's of degree 3. Then that means that the leading coefficient, what's in front of the x, 1, and because of this, the constant term, if there is nothing without a variable, it would just be 0. 12 in this case doesn't have a variable, so it's just x to the 0 power, so the degree would be 0 because it's called a constant polynomial. And the leading coefficient then we could just say is 12, and then the constant term is just itself 12. For the next one, notice that this has 0 times x to the 9th. So that really means that this term is not there because 0 times anything is 0. And if we look at this equation, notice that it also is not in order. If I were to write this in order, it would be x to the 8th power plus 3x to the 7th plus 2x to the 6th minus 4. In that case, now I know that my degree is 8. The leading coefficient, what's in front of the x that has the power of 8 is just 1. And my constant term is negative 4. You also need to know the names. A first degree polynomial is called a linear function, second degree quadratic, third cubic, fourth quartic, and fifth is a quintic function. Make sure you know those names. And again, a polynomial that consists only of a constant term is called the constant polynomial. So 12 would be a constant polynomial. In this chapter, we're also going to talk about long division. So we want to divide this polynomial by x minus 2 using long division. Remember, when you're dividing your polynomial, that means that this right here is going to be the part that uses your divisor, and that goes in front. So the next part is the dividend, which goes underneath. But before we do that, if I look at this equation here, I always have to make sure it is in standard form with the highest power first, and if I'm missing any zero placeholders, I want to make sure to put those in. And in this case, notice that the zero placeholders mean if you're missing any of the terms with the x to some power. So I have 3x to the fourth, and then I don't have an x to the third, so I need a zero placeholder. Minus 8x squared minus 11x, and then plus 1. So if you look at this, the first term's degree 4, the second term is degree 3, 2, 1, 0. Since I have them all in order now, I can know I'm okay to do my long division. And I should probably maybe move that down a little bit so I have more room to write. Okay. When you are doing your long division, you are taking the first term that you have right here, and you want to see how many times does x go into this first term, 3x to the fourth. Sometimes it helps me to do some work off to the side, which I'm going to do. So 3x to the fourth, I'm trying to see how many times does x go into that. So if you simplify this using your property of exponents, you get 3 and 4 minus 1 gives me x cubed. So that's how many times it goes in. Whenever you are doing long division, make sure that you line up your terms. I like to say put them in the homes where they belong. So this is the cubic home. So this gets lined up with my x cubed terms. So this would be 3x cubed. Now I take that number, and the next thing I have to do is multiply it. So I'm going to take the 3x cubed and multiply it by the x first and then line it up where it goes. So 3x cubed times x is 3x to the fourth, which we did on purpose so that we could eliminate that first term. Now I have to take this number and multiply it by the negative 2. When I multiply it by the negative 2, I get negative 6x cubed. And that's why we put the placeholder there, so we have a place for if that happens. And now the next thing we're going to do, after you multiply the terms, then you are going to be subtracting them. And this is key. So when you are subtracting them, I always change all of my signs and circle them to remind myself that I changed them already. And 3x to the fourth minus 3x to the fourth cancels out. And then we're left with 0x cubed plus 6x cubed, which becomes 6x cubed. And then the next step that you're going to do is just bring the rest of the terms down. So minus 8x squared minus 11x plus 1. And then we're going to do the process all over again. So I'm going to go ahead and erase these lines right here. Now I need to see the next term. So how many times does this x right here go into 6x cubed? So I'm going to do my math off to the side. 6x cubed divided by x, and that gives me 6x squared. So now I need to line this up with the quadratic term, so I'm going to put that in its home. It's positive, so I'm going to put plus 6x squared. And then I do my next step, which is multiply. So I take this 6x squared and multiply it by this term here, and then I'm going to multiply it by this term. So 6x squared times x gives me 6x cubed, which we did on purpose to match it up. And 6x squared times 2 negative gives me negative 12x squared. And then remember, we are going to change our signs, so this would be minus and this becomes plus. and then this term cancels out, which we did that on purpose. And then for the next part, when we do negative 8x squared plus 12x squared, that gives me 4x squared. And then bring down your terms. And then I'm going to erase that arrows that I drew there again, because now we're going to do the next one. Now I am trying to see how many times this x goes into 4x squared. So I'm going to do my math off to the side. 4x squared divided by x gives me 4x. I have to line that up with my linear term, so it's positive, so plus 4x. Now I take that 4x and multiply it by x first. So 4x times x is 4x squared, and line it up. And then 4x times negative 2 gives me negative 8x. And then the next step, don't forget to change your signs. So this would be minus, and this changes to plus. These two terms cancel out, and then I have 11 negative 11x plus 8x gives me negative 3x, and then bring down the 1. And then, of course, my process starts all over again. Now I'm going to do how many times does x go into negative 3x. So I do my math off to the side, and I get negative 3. So minus 3. Now I'm going to take that and multiply it by my two terms. So negative 3 times x gives me negative 3x. Negative 3 times negative 2 is positive 6. And then I need to change my sign. So this is going to become plus, and this becomes a minus. So it's a little bit harder to see. So negative 3x plus 3x cancels out, and we have 1 minus 6, which is negative 5. Now, because negative 5 degree is lower than our divisor, which is x minus 2, I know I can stop, and this becomes my remainder. So I have a remainder of negative 5. If we were to write this out the correct way, the way to do that would be 3x cubed plus 6x squared plus 4x minus 3, and then we're subtracting it from 5, our remainder, and our remainder goes over our divisor because we couldn't go in anymore. So this would be our solution. So that's the long division. Now, after long division in Algebra 2, then we learned about synthetic division. Synthetic division can only be used when the divisor x minus c is a polynomial of the first degree. If your divisor is not a polynomial of the first degree, you cannot use synthetic division. The degree of the quotient will always be 1 less than the degree of the dividend. So that means whenever you're finding your answer, it's always going to be 1 less than the degree of the dividend, which would be in this case right here, the dividend. This is the divisor, so 1 less than what you started with. Also remember, when you're doing synthetic division, it has to be in the form of x minus c. So your coefficient in front of your divisor has to be also 1. So if it's not, you have to change it so that it is 1. So in this case, if I look, we want to divide this polynomial by x minus 2 using synthetic division. And notice that this problem that we have here is the same as the last one. It's just that now we're going to go ahead and do synthetic division. And if you remember from Algebra 2, we have our box over here, and in our box goes whatever this 0 is. So the 0 for that would be 2. So that's what I'm testing, the 0. So 2. Then remember for your synthetic division that you have to make sure your terms are in order with no missing 0 placeholders, and then you take out the coefficients. So I'm going to rewrite it. So we have 3x to the 4th plus 0x cubed, because we need a 0 placeholder, minus 8x squared minus 11x plus 1. So down here goes the 3, 0, negative 8, negative 11, and the 1, if you remember from Algebra 2. Then the difference between this and long division is that instead of subtracting, we're adding, and you always bring down the first term, which is, in this case, 3. So then 3 times your number here, which is 2, would give you 6. And that goes here. And then you add 0 and 6 together, and 0 plus 6 is 6. And then you're going to do the next part. 6 times 2 gives you 12. And then you add these two numbers together. So when you add these two numbers together, you're going to end up with 4. And then 4 times 2 gives me 8. And then we're going to add 8 and negative 11 together, which gives me negative 3. And then negative 3 times 2 gives me negative 6. Add the two numbers together and you get negative 5. Now if you look at this compared to what we did with the long division, notice that these numbers here on the bottom are the same as what we have up here. It's just that all our x values are not in there. So that means if you take your x values out, you have to replace them back in. And right here it says the degree of the quotient will always be 1 less than the degree of the dividend. So this degree right here is a degree of 4. That means we're going to start with a degree of 3. So this becomes 3x cubed plus 6x squared plus 4x minus 6x cubed, sorry, minus 4x squared minus 3x minus 5. And you just go in order all the way down. So this right here, no, sorry, just kidding. Let's do that again. I'm gonna write it over here. So 3x to the third power plus 6x squared plus 4 x minus 3, and then our remainder is negative 5 over x minus 2, because this right here is always your remainder. So that's how you could have also done the problem with synthetic division. Knowing how to do long division is very important, especially for the next couple of chapters that we're going to get into, in order to solve some of the equations when we're doing some of the graphs and trying to find some things we need to be able to do the long division. So make sure you understand that. Next thing we need to talk about is the division algorithm. For this, it just means your dividend equals your divisor times your quotient plus your remainder. If the remainder equals 0, then the divisor and the quotient are factors of the dividend. In this case, let's just look at a real quick example. Something that we know is simple. So let's do 13 divided by 6. If I have this, I would rewrite this as 6 divided by 13, and I say how many times does 6 go into the 13? It goes 12 times, or 12 times, it goes 2 times. And then 2 times 6 is 12. Subtract the terms, and you end up with a remainder of 1. So I know that 6 and 2 are not factors of 13 because 13 is a prime number, but I can write it in this way. So this would be 13 equals h of x, which would be my divisor, which is 6, times my answer, which is 2, plus my remainder, which is 1. So 6 times 2 is 12, plus 1 gives me 13, so it checks out. If I had 12 divided by 6, 12 divided by 6 we know is equal to 2, so I know that 6 and 2 are factors of 12, because the remainder there would be 0. So next one says determine if 2x squared plus 1 is a factor of this polynomial equation. If I want to determine if something is a factor, then you need to look at the remainder. So let's go ahead and practice our long division, because right here I know I can't do synthetic division because it's not a divisor of a linear divisor, so it's an x squared, which is quadratic. So if I set up my terms over here, I have 2x squared plus 1, and I'm dividing it by, and I have to make sure this is order with no missing 0 placeholders. So this is a degree of 3, 2, 1, 0, so it is. So 6x cubed minus 4x squared plus 3x minus 2. Now what you could do is you could pause the video, and then when you're done, you could hit play and see, just kind of check your answer, see if you did it right. So for this, like we did last time, I'm trying to see how many times does this go into this first term. So I'm going to do my math off to the side. Whoops. Six x cubed divided by 2x squared. 6 divided by 2 is 3, and x cubed over x squared gives me just x. So I have to line that up and where it goes. And so this goes over the linear terms. Now I take that number and I multiply it by the 2 and by the 1. So 3x times 2x squared gives me 6x cubed, which we did on purpose. And then 3x times the 1 gives me 3x, and I have to line it up with this term, which is right here. Now remember, we are going to change our signs. This cancels out, and then this term is brought down, so minus 4x squared. This cancels out, so I'm going to put a 0 placeholder in, so plus 0x, and then this is brought down, minus 2. Now we're going to do the process over again. I want to see how many times does 2x squared go into negative 4x squared. Oh, I wrote that backwards. Sorry, negative. So when I do this, negative 4x squared divided by 2x squared, so negative 4 divided by 2 is negative 2. X squared over x squared is just x to the 0 power, and anything to 0 power is 1. So this is just negative 2. Now I take that negative 2, and I'm going to multiply it by 2x squared, and then I'm going to multiply it by the 1. So negative 2 times 2x squared gives me negative 4x squared, which we did on purpose, and then negative 2 times 1 gives me negative 2. And then when I change the signs, this would be plus, and this would be plus. That cancels out, and 0x is just 0x. This cancels out, and I'm left with 0. So because the remainder is 0, therefore I know that 2x squared plus 1 and 3x minus 2 are both factors of 6x cubed minus 4x squared minus 2. And we can write that using the division algorithm. So this would be So if I were to multiply these out, I would get this polynomial equation here. And so the question was determine if it's a factor, so I would say yes. 2x squared plus 1 and 3x minus 2 are factors of 6x cubed minus 4x squared plus 3x minus 2 because the remainder equals 0. All right, the next part is the remainder theorem. If a polynomial function f of x is divided by x minus c, then the remainder is f of c. So it has to be a linear term that we are dividing it by. So that means a power of 1 and no coefficient. So for this, it says find the remainder when you're dividing these two by using the remainder theorem. If I want to do that, then the remainder theorem states that if I take this and set it equal to 0, and I get x is equal to 1, I'm trying to test to see if 1 is going to, what it is going to be for the remainder. So now I take that 1, and I'm going to do 1 to the 87th power minus 2 times 1 to the 36 plus 8. When I do this, 1 to the 87 power is just 1, minus 1 to the 36 power is 1 times negative 2 is negative 2, plus 8. And when I do this, I get a remainder equal to 7. So that means that if I were to do long division or if I were to do synthetic division, my remainder would be equal to 7. And since it is equal to 7, that means that x minus 1 is not a factor of this polynomial equation, it also means that x equals 1 is not a zero of this polynomial equation. Next example, find the remainder when we're dividing by x plus 3 using the remainder theorem. So I'm going to take my divisor, set equal to 0 to figure out what I'm trying to test. So I'm trying to test to see what the remainder is going to be when I have an x value of negative 3. So when I plug this into my polynomial equation, and all I need to do is just then plug this into my calculator and see what it's equal to. So when you do all this calculations, you would get the remainder is 33. Because of that, I know that x plus 3 is not a factor of this polynomial equation because I didn't get a remainder of 0. Next is the factor theorem. A polynomial function f of x has a linear factor x minus a if and only if f of a equals 0, just like we were talking about for the remainder theorem. When you plug in that divisor number that you're trying to test, if you get 0, then you know it's going to have a linear factor of x minus a, so it just means it's a factor. If a is a solution of f of x equals 0, then x minus a is a factor of the polynomial equation. If x minus a is a factor, then you know that it's also a solution. So remember, when we're finding solutions to our equation, when we have a y value of 0, that means that these are the x-intercepts of our graph. So it just really means that they're the x-intercepts of the graph. So the next example says show x minus 2 is a factor of this polynomial using the factor theorem. So for the factor theorem, that means that if we take x minus 2 and I'm going to do x minus 2 equal to 0, so x would be equal to 2, I'm trying to figure out if I'm going to get a remainder of 0. So all I need to do then is plug it into my equation. So I would get 2 cubed plus 5 times 2 squared minus 2 times 2 minus 24, and if I get 0, then I know it's a factor by the factor theorem. So I'm just going to say that this right here, when I did f of 2, we're going to call this polynomial f of 2 would be equal to 0 you would find when you plug it in. So since you get a remainder of 0, that means that x minus 2 is a factor of the polynomial equation. So since f of 2 equals 0, then x minus 2 is a factor of x cubed plus 5x squared minus 2x minus 24. We could have also, since it didn't tell us how to decide whether or not it's a factor, we could have done synthetic division. We could have also done long division. So just to refresh our memory on synthetic division, in my box would go the number that I'm testing to see is a 0, which is 2, and then I have to make sure it's in standard form with no missing 0 placeholders, which it is. Then I put my coefficients in front, so 1, 5, negative 2, negative 24. Then we add our numbers together. The last number is going to be your remainder. Bring the 5 down, or the 1 down. So this becomes 1. 1 times 2 is going to give you 2, and 5 plus 2 gives me 7. And then 7 times 2 gives me 14, and 14 minus 2 gives me 12, and then 12 times 2 is 24, and negative 24 plus 24 is 0. So because my remainder is 0, that tells me that x minus 2 is a factor. That means I also know that this right here, if I were to write my coefficients back in, I would get x squared plus 7x plus 12. I know that this is also a factor of my equation. The next part says, let f of x be a polynomial of function with x minus r as a factor. If r is a real number, then r equals 0 of the function, so r is a 0 of the function is what that should say. And then it also means that r is an x-intercept of the graph of f. R is also a solution, or sometimes we call solutions roots, of f of x equals 0. And x minus r is the way that we write the linear factor. And we did some of that in Algebra 2. And also to note that there is a one-to-one correspondence between linear factors of f of x that have real coefficients and the x-intercept of the graph of f. So let's go ahead and do some more examples. For this polynomial function, we want to find the following: the x-intercepts of the graph, the zeros, the solutions when it's equal to 0, and the linear factors. So the x-intercepts of the graph, the easiest thing to do would be to first go ahead and plug this into my calculator. I'm going to pause it. Now that I have the equation in my y equals, I can go to my graph, and I'm going to hit zoom 6 to get a better look at the window. And I can see my 3 x-intercepts here. So second trace, I'm going to calculate my zeros, which is number 2. So something to the left, enter, something to the right, enter, and enter. So one of my zeros is negative 2.5. Now I'm going to do the next one. Second trace 0, so I have to do it again. It might be more helpful if I zoomed out so you could see a little bit better. So left bound, enter, right bound, enter, and then enter. And I get a value of 1. So if I zoom out, it's probably a little better, easier to see the graph. And then I'm going to change my x values to negative 10 to 10. That looks a little bit better. So second trace, I just need my last 0. So the last 0, something to the left would be below the x-axis. Down here, enter. Something to the right would be here, enter. And again, notice that those 2 arrows right there should be pointing towards each other, and then hit enter for guess. And the 0 is 5. So we had negative 2.5, 1, and 5. So the x-intercepts of my graph would be x equals negative 2.5, 1, and 5. So the zeros of f would also be the same thing. So the zeros are negative 2.5, 1, and 5. The solutions to the equation, when you solve this, are the same thing, because that is what happens when you plug those numbers in. You get 0 for a remainder. Thus, we know that they're going to be the solutions to your equation. So, or sometimes they're called the roots instead of the zeros. And that means x equals negative 2.5, 1, and 5. And then the last part is we want to write the linear factors. So writing the linear factors are when you're writing it as a binomial term. And to do that, you're doing the opposite of what we do when we solve. So in this case, 2.5 I know is the same thing as 5 halves, so I'm going to write that. So in this case, since it's x minus 2.5, I know that it would have to be x plus 5 halves, because if I were to solve this by setting it equal to 0, I would get x plus 5 halves equals 0, so x is equal to negative 5 halves. So you do the opposite. And the next term is going to be x minus 1 and x minus 5. And normally we don't like to leave our linear factor like this, because if you were to multiply this out, notice that your leading coefficient is 2. So just like when we do that factoring technique, I would swing that 2 in front. And this would be 2x plus 5. Oops, minus 1. So always look at your leading coefficient to determine whether or not you would have to change one of your zeros like we just did for the x plus 5 halves. So that would be my linear factored form. Next one says, find 2 polynomials of different degrees that have negative 2, 1, and 3 as zeros. So for this, I know that if these are my zeros, one equation that I could have would be f of x is equal to x plus 2, because that would give me negative 2 as a 0, x minus 1, and x minus 3. If I wanted another equation, I would just change the power. So maybe q of x is equal to x plus 2 squared times x minus 1 times x minus 3 to the 10th or something. Some students usually try to maybe change it by putting an x in front. If I put an x in front like that, that would be incorrect because that would mean I also have a 0 of x equals 0, which we do not from our original equation. So be careful not to do something like that. So I'm going to erase that because that's not supposed to be there. So those are two equations. The number of zeros of a polynomial degree n has at most n distinct real zeros. Some can be complex numbers. So if you look here, right here, this polynomial equation that we have has 4 zeros. So since it has 4 zeros, I know that one of them is distinct, which is the 5, which has a multiplicity of 2. We're going to talk about multiplicities and everything in the next couple sections, so we'll kind of skip over that for right now. Let's go to state the maximum number of distinct real zeros for this polynomial function. So if I have a polynomial function, how do I tell the distinct zeros? I look at the degree. So in this case, I have a polynomial degree 5. Because it's degree 5, I know that I have at most, so the maximum number of real zeros would be 5 because the degree is 5. So whatever degree your polynomial equation is, that's at most how many zeros you can have. The next question says, find a polynomial degree 3 with zeros 1, 7, and negative 4. So for this one, f of x is equal to, just like we did a minute ago, x minus 1 times x minus 7 times x plus 4. And if I were to multiply this out and put it in polynomial form, x times x would be x to the cube. Therefore, I would have a polynomial degree 3. Maybe if instead this said a polynomial of degree 5, if it was degree 5, then I would have to change my powers. So right now I have degree 3, so maybe if I made this a square, so that'd be 2, and then this one would be 3, 4, so I need another one, so maybe if I made this 3, so if this was degree 3, this would be an x cubed for the highest term times x, which would give us x to the 3, 4, 5th power, and that would be a polynomial degree 5. And that's how you would change it. Again, you can't just add x's in front because then that would mean you have another 0 of 0. The next example says x minus 3 is a factor of this polynomial equation. We want to find k. If I want to find k for this polynomial equation, I have to think about what we said in the problem. So the question says that x minus 3 is a factor of this. And remember, if it is a factor, then by the remainder theorem, I know that it's going to be equal to 0 when I have my x minus 3 set it equal to 0, so x is equal to 3. So I know that 3 is going to be 0 of my equation, and when I plug it in for x, it should be equal to 0. So I would do 0 equals 3 to the 4th power minus 5 times 3 to the 3rd minus k times 3 plus 18 times 3 plus 18. The only thing I need to do then is to solve this equation. So when I combine like terms and doing everything, I would end up with, and you know what, I think I forgot the square there, so that should have been a squared. So let's go ahead and put this as a squared here. Sorry about that. When I do that, I end up with negative 9k plus 18 equals 0. And then when I solve this equation, I get k is equal to 2. And that would be my answer. Of course, you could always check your answer by plugging the polynomial equation into your y equals and then seeing if you have an x-intercept of 3, or if you plug 3 and look at your table, you should get a y value of 0.